Well, hello everybody. Dave here today to continue our lessons on electrostatics with the idea of electric potential energy and how it relates to this other concept known as electric potential. Now, in previous studies, we learned about gravitational potential energy and the idea that if we took a massive object and moved it away from the center of mass of the mass creating the gravitational field, what would result is the object would have potential to move in that field. Well, this is very much a similar idea when we're talking about electric potential energy, except instead of dealing with a massive object, we're dealing with an object that has charge. And because it has charge, depending upon the charge of the object creating the electric field, this object will have potential to move towards that charge or away from the charge. So when we're dealing with a non-uniform field, we're dealing with something that has a different magnitude and direction depending upon the proximity to that electric field producing charge. Now, in the past, when we've talked about moving an object in a field from one point to another, we've talked about it in terms of work and energy. And so to remind ourselves, work is equivalent to either the change in energy or the applied force on the object times the distance traveled. Now, in our case, we can actually deal with it in terms of the potential energy because we don't care about the path that we take to get from point A to point B. In this case, because the forces are conservative, we're considering it to be path independent. So what that means is we can take our change in energy and equate it to the change in potential energy and keep that equal to the applied force times the distance. So what do we do now? Well, in the case of a point charge, we know that no matter where we move it in the field, as long as we're moving it in a radial direction, that distance is going to be the distance away. The applied force in this case is going to be the electrostatic force between the charge that's producing the electric field and the charge that we're moving itself. And so what we get is an equation where the potential energy is equal to kQq over r squared times the distance, which in this case is r. Now, some of you may be asking, well, where did the delta go? Well, in this case, we're going to imagine that we take a charge and we move it from infinitely far away so that there is no initial potential energy present. We've done this in the past with gravitational potential energy when we talked about things like an asteroid moving in from infinitely far away. The idea behind this is the charge is so far away that there is no interaction between it and the field produced by the field producing charge. So you'll notice again that instead of labeling it as D, I've labeled it as R because of the non-uniform nature of this field and the fact that from a point charge, it is produced radially outwards, which means that no matter where you are in that orientation, as long as you are a distance r, it doesn't matter if you're north of it or south of it, you're still going to feel the same field strength. So that means that one of the r's cancel on the denominator of the electrostatic force, and we end up with our equation for potential energy to be kQq over r. Now, with my notation, you'll notice that I've given a large q and a small q. Well, for me, I like to keep things organized with some sort of convention. Now, subscripts are a great way to go, but in my case, I like large Q to represent the charge that is producing the electric field and the small q that represents the charge that is interacting with that field. Now, you'll notice again that this looks a lot like the equation for potential energy when we were dealing with gravitational effects. Well, the reason for that is, in the case of gravitation, there's only one direction that an object can go. There's only an attractive force when it comes to gravitational force. However, with electrostatic force, we know that depending upon the polarity of the charges, there could be an electrostatic force that attracts the objects or an electrostatic force that repels the objects. The key idea here is you are going to have to determine the direction of motion based upon the polarity of the objects themselves. So let's do an example that applies this concept, and we're going to take a 4 microcoulomb charge from very far away into a distance of 1 meter away from a 6 microcoulomb charge. Now, in this case, because the 4 microcoulomb charge was infinitely far away, we are considering this to have no initial potential energy because there was no meaningful interaction between the two charges. However, to move it to within 1 meter of the 6 microcoulomb charge, now there has to be some energy required to do that because these charges are both positive, which means they would naturally want to repel each other. So when we talk about this in terms of the work required, we know that there is no initial potential, which means the work can be found by only calculating the final potential energy. And we just derived an equation that gives us this to be KQQ over R. Now it's important to recognize that we are dealing with point charges and only point charges. If we were dealing with a uniform field, we would be dealing with a different type of formula to give us the work being done. So recognize the fact that we are just focused on the fact that these are point charges alone. So now we can substitute in our values for the potential energy, and we know that K is the electrostatic constant of 9 times 10 to the 9. We have our two charges in terms of coulombs, not micros, so we know that micro is 10 to the minus 6. And we have a distance of 1 meter away to give us a final amount of energy of 0.216 joules. So what this means is that it takes 0.216 joules of energy to move that charge to within 1 meter of the electric field producing 6 microcoulomb charge. Now there's a couple of important notes that I want you to understand before we move further through this lesson. The first is understanding that potential energy has always been a scalar quantity, which means we don't need to do vector addition when we're doing anything involving potential energy. There will be questions that sure look like questions that you've seen in the past when it deals with electric fields. However, an electric field is a vector quantity, which means there would be some sort of vector addition to do. With potential energy, it's a scalar quantity, so just add the values up. And because of that, we're going to use the negative and positive signs of the charge when we calculate the potential energy. This is different than the way that I teach dealing with electric fields, because I like the free body diagrams to do the explaining of the direction of the net field that's produced with multiple charges. When it comes to potential, the easiest way to deal with this is just to use those charge negative and positive signs. So if we're talking about two positive charges, we know that those don't naturally want to come together, so we would expect it to take a positive amount of work to get us together. If we're talking about a negative and positive charge, the negative would want to be attracted by the positive charge, which means we should end up with a negative potential. And again, this goes back to the understanding that when we're dealing with positive, there is work being added to the system. When we're doing negative, that means that there is energy being released from the system, or at least transferred into a different form. So let's do an example that involves this difference in polarity. And we'll do a similar question to the one we just did, except this time instead of moving a positive charge into a distance, we're going to move a negative charge in. And so in this case, we have a negative 7 microcoulomb charge that we're going to move from very far away into a distance of 0.5 meters away from a 5 microcoulomb charge. Well, in this case, we know that a negative charge would want to move towards a positive charge. They're different polarities, which means they should attract each other. So what that means is when we calculate the work to be done, it should be a negative value because it wanted to move towards the positive, so it should be releasing energy in order to do so. So when we calculate this now, we use the exact same concept as before. We know that we have equated our initial potential to be 0 because of that lack of interaction initially between the two charges, which means that to calculate the total work done, we're simply finding the final potential energy of KQQ over R. This time when we substitute things in, you'll notice that the negative 7 microcoulomb charge has been substituted in as a negative value to give us a final quantity of work to be negative 0.63 joules. This is an important sign to understand. The fact that when we bring a negative charge towards a positive charge, it will require negative work to do so because it is releasing energy, or at least converting it into some other form. Now there is an important quantity in electrostatics that we have to understand, and it's this idea called electric potential. Now this is different from electric potential energy, however these two are related to each other in the following way. The definition of electric potential is the amount of work needed to move a unit of charge from a reference point to a specific point inside an electric field without producing an acceleration. Said differently, it's defined as the work per unit charge required to move this positive test charge from an infinite distance away into a distance r. Now, we will define electric potential with the capital letter V because the units of electric potential are something that hopefully you've heard of before. They are volts. And so V is equal to the work per unit charge, which we know from our previous experience with point charges. The work to move a point charge from infinitely far away into a distance r is simply just the potential energy at that distance. And so if we take our equation for potential energy and divide it by this unit charge Q, you'll notice the reason why now I label things according to a capital Q and small q. Because we can cancel that Q and we end up with our equation for electric potential to be V is equal to KQ over R. And so simply put, the work required to move this charge into a distance R is related to the actual electric field being produced by this capital Q charge. There's a couple of notes that are important when we're using electric potential. We know that we're talking about moving a positive charge, which means that the sign convention for electric potential is that positive charges will move towards areas of low potential or away from a positive charge. A negative charge should move towards area of high potential because we're dealing with an object that would be attracted towards a positive charge. And as I've said previously, the units for electric potential, we're dealing with work per unit charge. Well, work is in joules and charge is in coulombs, and so a volt by definition is a joule per coulomb. So let's do an example problem to understand how to apply this concept. We have 3 point charges and we want to understand what the potential is at point P. Now notice that it's not asking for the potential energy, so right away you can understand that we're not dealing with potential energy directly, we're dealing with electric potential. And so electric potential is again a scalar quantity, which means we don't have to do vector addition. But what we will do is the concept of superposition, the idea that the total potential at point P is the sum of the individual potentials produced by the individual charges present, which is why, if you see the mathematics that we're doing here, I'm going to calculate the electric potential created by each of the individual charges. You'll notice that, like we did with electric potential energy, I will use the negative sign to help me understand the sign convention of electric potential. And so in the case of V3, you'll see that we get a negative electric potential value. So to find the total potential, we simply take the sum of the 3 voltages to end up with a value of 694,000 volts. It's important to recognize, like we did with electric potential energy, that there is no vector addition. The constant mistake that is made is everybody focuses so much on dealing with electric force and electric field calculations that when we get to these scalar quantities, we continue to think that we need to do something like the Pythagorean theorem. I encourage you strongly to understand the language of the question and based on that, the physical properties of that quantity, which in this case means scalar quantity only. Now, one of the properties that's going to be important to understand with electric potential is when there is a potential difference from point A to point B. You're going to see in future studies of uniform fields and electric circuits that a potential difference is what will actually drive things like current. And so when we talk about the potential difference, instead of referring to just the final potential energy per unit charge, we're going to talk about the change in potential energy because we no longer necessarily are moving from a point infinitely far away into some distance r. However, for the sake of the next question, we are going to keep it as a point charge and save the more uniform field applications for a later lesson. So let's deal with an example that allows us to find the potential difference between 2 points A and B. Remember that these are points in space, so what some people will do incorrectly is they will think, hey, this looks like a right triangle. Let's find the distance between A and B using the Pythagorean theorem and then calculate potential that way. But here's the thing that I need you to remember. Electric potential is a scalar quantity, and it's related to the concept of work. And if you remember from previous discussions of work, because all the forces at play here are conservative forces, we are path independent. So it doesn't matter how we get from point A to point B. It's the fact that we get from point A to point B that's the most important. And so when you see us calculate the potential difference here, we are simply calculating the potential at point B and subtracting from it the potential at point A. When we substitute in our values for that, we get a value of 72,000 volts. So I really want you to recognize the fact that this is not a vector quantity. You do not change this into some sort of Pythagorean theorem case. There is a visual that can be useful when we're trying to find the electric potential difference, and that's this idea known as an equipotential surface. If you look at the bottom left, you can see that there's a positive test charge. The red lines that are pointing radially outward are representing the electric field that is generated by that charge. Well, the concentric circles that are radiating outwards from this positive charge are the equipotential lines. And what that means is, if we look back to our definition of electric potential, we know that it's proportional to 1 over R. What that means is at any point on those circles, it has the same electric potential. But the difference between one circle to another is our electric potential difference. So remember that we don't care necessarily about the path from point A to point B, but understanding that these equipotential lines exist allow us to quickly find the difference between, say, circle 3 and 1. You'll also notice that the distances between the circles are becoming larger, and that again is the nature of this 1 over R proportionality. One thing important to note is when you are drawing equipotential lines, they are perpendicular to the electric field lines. So when we look at a dipole, you can see the electric field lines that we've drawn there and how the equipotential lines are drawn relative to those. Again, they're always perpendicular to those electric field lines. But you'll notice that there's this line right down the middle that represents 0 potential. Now that may be confusing, but let me try to explain with the diagram above. We have to remember that our definition of equipotential was based upon moving a positive test charge. And we further define the idea that when we have a positive test charge and we move it towards a positive test charge, that's going to be moving towards a higher potential value. If we look at this 3D model, you can see that there is this mountain and there is this valley. Well, this is the classic way that we think about equipotential surfaces, is that they are in fact topographical maps of the potential associated with the charges. So in this case, the peak is representative of the positive charge, and the one that is dipping negative is in fact the negative charge. So if we think about this 3D model like it's a physical mountain, and we take an object and we put it at the red peak and we let it go, it would want to roll down that mountain, and when it gets to that 0 potential, it's not that it's incapable of moving, it would continue to roll down towards that purple valley. Well, this is very similar to the way that charges move, because if we have a charge at the red peak and we let it go, it would naturally fly away from that positive test charge. When it got to the middle, it would be considered 0 electric potential, but at the same time, it would still want to continue moving towards the negative charge. And so this 3D model and the dipole equipotential lines that we've drawn are a great way to think about equipotential lines, is that it is a mountain and objects are being moved towards the peak or away from the peak depending upon the polarity of that test charge. So everybody, that's a quick lesson on electric potential energy and electric potential. Again, it's worth understanding the difference between the two and how they are related, and of course this idea of potential difference and its usefulness that will certainly be more obvious in later lessons. So good luck with your practice problems. We'll see you again.